everyone. In this video, we're going to talk about Feynman diagrams. Now, Feynman diagrams are a very useful way to pictorially represent what are very complicated calculations. And so they're a way of organizing your calculations in a useful way. And ultimately, each piece of your diagram is going to correspond with some mathematical quantity. Now, to understand the mapping between the diagrams and the mathematical quantities requires a full class in quantum field theory. So we're not going to see that. And instead, ultimately, you'll just learn what that mapping is and use it. And actually, in this video, we won't even get there. For now, we're just going to think about drawing the diagrams and thinking a little bit about what they mean. So these diagrams are going to help us to calculate different types of processes in particle physics. So for instance, we might have a decay where we start with one particle and then some number of particles comes out, 2, 3, 5, however many. And in the lab, all we see is this incoming particle, which is our initial particle, and then our outgoing particles. And we have no idea what happens in between because we don't actually observe that. In our particle detector, all we know is we started with this particle, and then these particles came out, which we detected. And we don't actually see the intermediate process. Same things happen if we consider scattering. And so maybe we start with two particles and then they collide, and then we have two particles coming out. So this would be 2 to 2 scattering. We might have 2 to 3 scattering. Turns out that two particles can collide and then have 3 particles come out, right? This is really getting into the quantum nature of what's going on here. This is not like billiard ball scattering that you did in intro mechanics class, right? So again, in the lab, all we see is the incoming particles and the outgoing particles. And what happens in the middle is never observed. And in quantum mechanics, when we have a situation like this where we don't really know what happens in the intermediate steps, the way to calculate the probability for this particular decay or this particular scattering or whatever it is to occur is to sort of assume that everything that's possible to have happened in the intermediate steps did happen. No matter how complicated, you assume all possibilities potentially happened. And with each of those possibilities, we would associate a particular amplitude. And then if we want to say, what's the likelihood of this particular decay happening? We add up the amplitudes for the individual things that could have happened in the intermediate steps. And then we square that. And by that, I mean, we multiply it by its complex conjugate. And then we end up with the probability for this particular decay process. It turns out that the number of things that could happen in the intermediate steps is infinite. There are so many things that could happen. Now, fortunately, if we're thinking about at least electromagnetic interactions that might occur and weak force interactions that might occur, the more complicated the intermediate steps are, the sort of smaller amplitude you end up contributing. And so we can actually really complicated intermediate processes that only involve the electromagnetic and the weak force. We can sort of ignore those because they effectively contribute 0 to our total probability for this particular process to occur. Now, things get more complicated when you deal with the strong force because the strong force is strong. And so it turns out that we can't just make this argument that more complicated things go away. So we're going to have to think about the strong force in a way that is different. But there still will be ways that we can think about it. But for now, for the back of your head, you should just think that more complicated intermediate steps in general are going to contribute less So that means the simpler diagrams, which will correspond to simpler calculations, which we can fortunately do, are going to be the most important ones. Okay, so I said we're considering, for instance, a particular decay. We have some initial particle, and then we want to say, what's the probability this particle is going to decay to this other particular set of particles? And we don't know what happens in the intermediate. All we know is what we started with and what we ended with. How can you determine what possible things might happen in the intermediate? Well, it's going to depend on the type of particle you start with and the forces that it interacts with. So for instance, if you start with a charged particle, then that's going to interact with the electromagnetic force. And so we know if we start with an electrically charged particle, the electric force might be at play. A charged particle might also interact with the weak force. And so maybe the weak force will be at play. However, if you start with a lepton, which is to say like an electron is a lepton, this does not interact with the strong force. And so then we know the strong force won't be at play. And so what we want to do is we want to think about all of the different intermediate things that could happen given the constraints of the types of particles you're starting and ending with. And the way we're going to build up all of these different possibilities is by using a finite set of what are referred to as fundamental vertices. And then any allowed Feynman diagram is built out of these fundamental vertices. And the fundamental vertices are going to do things for us like guarantee that only charged particles are interacting with the electromagnetic force. A neutrino should not interact with the electromagnetic force because it's not charged. And so if you only build up your diagrams by using these fundamental vertices, then you know that you're sort of following the rules of the game of particle physics, and only the allowed, only if you have a certain particle, only the allowed forces that should be at play will be at play. Also, these vertices are going to do things for us like conserve charge, so electric charge. They'll also conserve other types of charge. So it turns out color, when we talk about the color of quarks, that's sort of like the analog of charge when you think about the strong force, that's going to be conserved. So if you only build up your diagrams with these allowed fundamental vertices, which I'm about to give you, you know then that all of your conservation principles are going to be obeyed as they should be. Okay, so let's to make this a little more tangible, let's start to think about our fundamental vertices. So the first is the electromagnetic vertex. So for the electromagnetic vertex, our particle, which propagates the force, the electromagnetic force, is the photon. So this little gamma is representing a photon. And what we could have is a charged particle coming in, interacting with the photon, and then another charged particle coming out. We're going to have arrows on these diagrams. You'll notice it's always going to be one arrow coming into the vertex and another arrow going out. We'll talk about the meanings of these arrows in a minute. In short, they're going to keep track of whether these particles are particles or antiparticles. So because the only charged particles interact with the photon, this thing on this vertex, which appears to be coming into the vertex, can be any charged particle. So this might be an electron, it might be a positron, although the way my arrow is, it looks like it's an electron. Again, we'll understand the arrows more in a minute. It could be a quark. Quarks are charged, right? So the particle that's coming in that's attached to this straight line can be any charged particle that you like. And then on the other side, what we're going to have going out is the same particle. Which is to say a particle with the same flavor. Flavor is sort of a funny word that particle physicists use. That's really talking about if you have a particle that has the same name generally, it's the same flavor. But like antiparticle partners are the same flavor. So for instance, so this is a bad example because I just said it's the same name. So an electron and a positron, they're antiparticle partners. So they have the same flavor. So they're different particles, but they're different particles with the same flavor. Same with the up and the anti-up, right? The up and the anti-up are the same flavor particles because they have the same name is one way to think about it, even though it's an up and an anti-up. So anyways, so the photon does not allow us to change the flavor of the particle, but it will allow us to change a particle into its antiparticle, and it's going to depend on the orientation of our diagram. So when we build up, so I said this is some vertex that we're going to use as sort of a building block to build more complicated diagrams connecting our incoming to our outgoing particles. We can rotate these vertices in any way we like. And the direction of these arrows relative to the direction of time is going to specify whether this is a particle or an antiparticle. So let's look at sort of the four primary ways we can imagine drawing this diagram. And so I'm always going to, in all of these, time is going to be propagating to the right. So we're thinking of time moving forward to the right. So our incoming particles are coming in from the left, our outgoing things are going to the right. So we can draw this diagram in four ways. So we could draw it the way I just did. And to be concrete, let's say this incoming particle is an electron. I'm now labeling my lines with E to represent electron. Time is moving to the right. So what you should think is particles flow in the direction of time. Antiparticles flow against time. This shouldn't necessarily make you think that the electron or the antiparticle, so in this case, the positron, is actually flowing in reverse time. I mean, there are ways you can think about that. But right now, you should just think of it as if the arrow is going backwards in time, or it's pointing against time, then that's going to tell you it's an antiparticle. So in this first example, sorry, I don't know what just happened there. In this first example that we have here, both of our arrows are flowing with time, so that tells us they're both electrons. But we can rotate this vertex any way that we like. So, for instance, we could rotate it 90 degrees, so it looks like this. We have an electron coming in, and now on this upper leg, we have our particle, but the arrow is sort of going to the left, which is the opposite direction of time. So we interpret this lower particle as an electron, and the upper particle as a positron, which is the antiparticle partner of the electron. In the first diagram, this one over here, right, both of my arrows were flowing with time. So both of these were particles, not antiparticles. And so this first diagram, what it's sort of representing is an electron coming in and scattering off a photon, is one way to think about it. Whereas in this second diagram, because time is going to the right, what it looks like it's representing is an electron and a positron coming in, annihilating each other, and turning into a photon. Right, so that's what these fundamental vertices look like is going on. We could also consider this diagram, which looks like my first one, except I've just reversed my arrows. So I've sort of twisted my diagram. So again, you can sort of rotate or twist your diagram in any way you like, and it's all going to be allowed. And I'm just really giving you some examples here of possible ways you could rotate or twist your diagram. So here I've twisted it, and now both my arrows are going to sort of to the left, so against time. So these are actually both positrons. Notice with all of these, I'm just labeling E's. I'm not putting like E plus or E minus. I mean, you could do that if you like to really emphasize. But here, what I'm trying to emphasize by notating it this way is it's the particle flavor is staying the same, and E is like sort of telling us the flavor. So these vertices don't change flavor. And then once you know the flavor, you just need to determine if it's the particle or the antiparticle partner. And that's determined by the directions of these arrows. And then a final one that I might draw is one where we start with our photon, and then we have these arrows where it looks like our photon now is spontaneously pair producing an electron and a positron, where this top one has the arrow going against time, so that's the positron, and the lower one is the electron. So this looks like pair production. So this is like annihilation, and this looks like pair production. And these other two look sort of like just scattering off of a photon, or you could say it's absorbing the photon to gain more energy or something. And so you could do this. I drew all of these with the example of electrons, but again, any charged particle, you could create these vertices with. And you can sort of rotate them or skew them in whatever way you like. And it's all sort of allowed. So because, you know, again, what we're thinking about is ultimately we're starting with diagrams that look like this, where you have some incoming particle or multiple particles, and then we're going to want to sort of rotate these vertices in weird ways in order to get them to fit together. Right? Because again, these vertices are like our building blocks. So you can sort of rotate them and stretch out legs if you like. But the rules of the game for this electromagnetic vertex, again, are that it's one leg is a photon, 2 legs are your charged particles, 1 arrow always goes in and 1 arrow always goes out. So maybe I should even write that down. 1 arrow always in and 1 always out. And what that's doing for us is things like charge conservation. So for instance, if I drew this diagram where I have both my arrows going into the vertex, then it looks like I have an electron and then a positron and a photon. So somehow the electron is turning into a positron. But this is breaking charge conservation. We're starting with some negative charge. Remember, the photon doesn't have a charge. It's a neutral particle. So we just have this electron somehow interacting with a photon, and then somehow we're gaining positive charge and turning into a positron. So this is bad. And so this is where I'm saying, if you stick to only building your diagrams out of these fundamental vertices and following the rules that are associated with each vertex, then things like charge conservation are just automatically going to be satisfied by your diagram, no matter how complicated it is. Okay, so that's our first diagram that we might consider. Let's look at our second diagram, which would be for the strong interaction. So only quarks and gluons interact with the strong force. This phrasing may seem a little weird because the gluon sort of is the strong force, right? The gluon is the particle that carries the strong force. The reason I'm phrasing it in this way that's a little confusing is because gluons are actually self-interacting. And that's because, so with the photon does not have a charge. And so when we look at the rules of the game for our electromagnetic vertex, we could not have, the photon is not a charged particle. So we couldn't have the particle attached to these straight lines being the photon because it's not a charged particle. So we can't do that. On the other hand, when we were talking about the strong force, the equivalent thing for the strong interaction, the thing that's analogous to electric charge for the strong force is color. So color is this weird thing that is confusing to a lot of people because it's not really representing like the color of particles, like in terms of like visible spectrum or something. The color is actually the analog of charge, electric charge, but for the strong force. So color is like a strong force charge. And the reason we think about it in terms of colors as opposed to like with charge, we just have the fundamental charge, and it could be like positive or negative of the fundamental charge or some fraction of it if we're dealing with quarks. It turns out the strong interaction is sort of more complicated than that. And instead of just having a positive or a negative version of the strong interaction, there's sort of like three axes that we want to consider. And so we have sort of the redness axis, the blueness axis, and the greenness axis, greenness. And so color is sort of a useful way to think about it because we have these three axes instead of just talking about whether it's positive or negative. Okay, so anyways, only, I guess another way of phrasing this is only colored particles interact with the strong force. And the only colored particles are quarks. And then it turns out gluons themselves are going to actually have two colors associated with them. So gluons are going to be self-interacting. So we actually have a couple different types of strong interaction vertices. So there are quark interactions. Here we have a diagram that looks very similar to our electromagnetic vertex, except now we draw this sort of curly line, which is representing a gluon. The other one was a squiggle. This one looks more like a spring, right? This is our gluon. Again, we're going to have arrows attached to our straight lines, which are going to tell us whether it's a particle or an antiparticle. And in this case, specifically a quark or an antiquark. So here we have any quark coming in, and then the same quark going out. All right, so again, we would say that this vertex doesn't change flavor because in this particular orientation, the up will stay an up, or at most it'll change from an up to an anti-up if we rotate the vertex in the appropriate way. We also have gluon self-interactions. So we actually can also have vertices that look like this. Where these are three gluons interacting with themselves. And actually, so far, all of our fundamental vertices, you'll notice it's three lines coming together. You should never draw an electromagnetic vertex where somehow there are four lines coming together. It's always three, a photon and then two charged particles. Same with the quark-quark interaction, it's three lines coming together, two quarks and a gluon. We can have this vertex of three gluons interacting, and then we actually have, and this is our only sort of four-leg vertex, which you can actually have four gluons interact directly like this. Okay, we aren't really going to deal with the gluon-gluon self interactions right now. We're going to focus more on the quark-quark interactions, but I think it's important to note because this is a big difference between the strong interaction and the electromagnetic interaction, which is that gluons self-interact. So we get these additional fundamental vertices which are allowed, which are the gluon self-interaction fundamental vertices. Okay, so like in the previous case, we can rotate these vertices to fit them in our diagram in whatever way we need or want. And so we'll look at sort of four possible orientations. And for concreteness, we're going to say our particle is an up. So if we draw it just like this initial example I gave, the arrows are flowing with time. So these are both indeed up particles. We could also draw a diagram that looks very similar, where the arrows are flowing against time, and then we know that these are anti-ups. Or again, these apply to any quark that you like. So it could be two bottoms in the first case, a bottom interacting with a gluon and then sending that bottom out, or it could be an anti-bottom scattering off a gluon and staying an anti-bottom. Or we could rotate them 90 degrees. Again, we have one arrow in, one arrow out always. And so this is an up and an anti-up, annihilating and turning into a gluon. Or we could sort of flip this diagram, start with a gluon, and then pair produce an up and an anti-up. Oops. Oh, I just made the big mistake that I'm not supposed to make, right? I have two arrows going into my vertex. So what we want to do instead is have this arrow going out. And so this is a gluon pair producing an up and an anti-up. So just like with the electromagnetic interaction, we can have these different orientations, which depending on the flow of the arrows, whether it's with or against time, are keeping track of whether the particles are particles or antiparticles. And again, what this is going to do for us in part is to ensure charge conservation. And there I am literally talking about electromagnetic charge. I will also note that these vertices are also going to conserve color of our quarks and our gluons. So again, quarks are going to be objects that have some color. Gluons are going to be objects that have two colors, which will be one color and one anti-color. And so I don't want to go into too much detail about this, but for instance, if this up quark is a red up quark, and you should really think about the different colors of up quarks as being like, they're just different particles, actually. They're particles that have the same flavor, but they have different colors. So it's just like, you know, the electron and the proton, they have the same magnitude of the charge, but they're different particles. I mean, they're definitely different particles. I mean, the proton's also composite. So, okay, so maybe that was a bad example, right? They're different particles. They have different charges. So in a way, we have, for our up quarks, we have three different versions of the up quark. There's red, green, and blue up quarks. So if we start with the red up quark, this gluon might be a blue anti-red. And then that would tell us the outgoing up quark is going to be a blue. Did I do that right? anti-blue, but this can't be. Oh, maybe I shouldn't have gone into this because now I've gone ahead and confused myself. Anyways, at this point, talking about their color conservation is a little bit, I messed that up. That's not quite right, but it's something like that that's going on in the background that is sort of beyond the scope of where I wanted to get to in this video. Because for now, all you need to know is we have an up coming in and an up going out. So they're the same flavor. They could possibly change color because of the interaction with the gluon. That's all I was really trying to get at with that. Okay, so the final type of vertex that we'll talk about are those associated with the weak interaction. And there are actually 3 vertices here, right? Because the weak interaction could mean W plus minus or Z, right? We have 3 particles associated with the weak interaction. So W plus and minus can sort of be treated in similar ways. And the thing that you just always have to make sure is whatever you're drawing conserves charge. The Z is a little different because it's neutral, but again, it's just going to always make sure that it conserves charge. For W plus minus, I want to think about the vertices for leptons and then for quarks separately, because the rules of the game are a little different whether you're talking about leptons or quarks, right? Both leptons and quarks interact with the weak force. So because the W plus minus carries charge with it, 1 unit of charge in particular, then that means by definition, the flavor of the particle must change because charge needs to be conserved. So for instance, if I have a lepton coming in, which I'll write as L, and it's interacting with W plus or minus, then this must be a neutrino that's coming out. And so what's happening is the charge from this lepton is being transferred to the W plus or minus, and then the neutrino that is going out. And notice I put sort of a sub L on my neutrino because this is specifically the neutrino associated with the initial lepton. Right? And again, we can take this vertex and rotate it any way we like. So maybe we're starting with a neutrino and it turns into a lepton. But the rules again are the same. We always have 1 arrow going in, 1 going out, and the arrows are going to tell us whether it's a particle or its antiparticle partner. And the thing I just want to make sure it's clear that even though, for instance, an electron might be changing into a neutrino, specifically the only neutrino that it seems nature will allow is that the electron needs to turn into the electron neutrino specifically, or the muon needs to turn into the muon neutrino specifically. Quarks are a little more complicated in a way, because we're going to start with some quark coming in. And then what's going to go out is a different quark. And what the quark that comes out that's the different quark just needs to again conserve charge. And so for instance, we might start with an up. And then if we think of our W particle as carrying away a unit of positive charge, so this has charge plus 2/3, and then our W, we'll call this a W plus, so that it's taking away a full positive charge. Then this quark over here must have charge minus 1/3, right, in order for charge to be conserved. But this quark, there are 3 quarks that have charge minus 1/3. This could be a down, this could be a bottom, this could be a strange. And unlike the leptons, where you had to sort of stick in your lane, an electron only turned into an electron neutrino, the up quark doesn't have to turn into the down quark. It has a chance of turning into the bottom or the strange quark. So charge needs to be conserved, so it has to be one of those 3. The probability that it changes into the down quark, if you're starting with the up, is the down quark is the most likely. But it turns out any of the 3 are possible. And so the weak interaction for quarks ends up being a little more complex for this reason. And so at this stage, you really just need to make sure that charge is being conserved. Okay, so that's W plus minus. And again, I'm not going to go through all the rotations of the diagrams. Again, with all of these, you can rotate them in any way you like. And the direction of the arrows tells you whether it's a particle or an antiparticle. And so you can have things like annihilations or pair productions going on. The Z is a lot easier, actually, because it looks much more like our electromagnetic or gluon vertices. So we have a Z, which is neutral. And we start with any fermion. And then we have the same fermion. So again, this does not change flavor. So if we have an electron coming in, that electron is going out. It's absorbed some Z particle or it's interacted with some Z particle in the intermediate, but otherwise the electron has not changed. If we rotate this diagram, it could be, again, like an electron-positron annihilation turning into a Z particle. So that's allowed. So by the same, I mean, it could switch between a particle and an antiparticle, but otherwise it's the same flavor of particle. And so that's our Z particle, or our Z interaction, excuse me. Right, I mean, it is also a particle. So this is how particles interact with the Z particle. And that's sort of it for our fundamental vertices. And so we have this finite set of fundamental vertices, all of which have rules associated with them. And then what we do when we build up Feynman diagrams, and we want to think about if we have one particle decaying into some other ones, we just think about how we can rotate these diagrams and snap them together, attach the legs together. And we can't, a leg can't, like a photon can't spontaneously change into a gluon or something, right? So the only way particles are going to change is via these vertices. And things like the direction of the arrow is going to need to stay consistent. And then following those rules, we attach these fundamental vertices to each other in different ways to build up more and more complex diagrams. So I don't want to do too many examples because this video is already really long enough. But let's look at an example. Let's say we have an electron and a positron scattering. So actually, I drew it as a vertex right away. I shouldn't have done that. What I want to say is I want to have an electron coming in and a positron coming in. So I've already attached arrows to my legs to tell me that this is an electron and a positron. Again, the arrows aren't like telling us the direction the particle is moving. It's just telling us whether it's a particle or an antiparticle. And then let's just say, let's consider the electron-positron scattering. And so maybe I also have an electron and a positron going out. Sorry, I want a positron coming out. And so we want to think about all of the different ways we can connect these 4 legs together by using our fundamental vertices. And so, there's some simple ways. So for instance, they can sort of directly connect like this, turn into a photon, and then directly connect like that. All right, so we have our positrons up here, our electrons down here. And what this is suggesting is that one of the possible intermediate things that could have happened in this scattering is the electron and the positron annihilated, turned into a photon, and then that photon pair produced a new electron and positron pair. So this is a possible diagram. Or maybe something more complicated happened. Maybe we have our electron and positron. Again, let's say they start by turning into a photon. And then maybe they pair produce first an up quark and an anti-up quark, which usually we'll use a bar for antiparticles. Right? This is another fundamental electromagnetic vertex. So we have this guy going forward in time, this guy going backwards in time. So it's just, I've just attached on a different one. We still somehow need to end up over here with our electron and our positron. And maybe I'll have this side look sort of the same as it did before. Maybe they at the last step is sort of a pair production. How can I now attach these things? Well, I can add one more vertex to these, where now I attach these legs. And again, my arrows need to go the same way. This still needs to be an up. And if I attach two lines together, the particle, again, can't spontaneously change mid. But I can sort of attach them in this way. And so again, so what do I have here? I have this initial vertex, and then that line coming out of my photon has given me a second vertex, and then a third vertex, and then my fourth vertex. And I've just connected them in ways that are consistent. And now something much more complicated has happened in their intermediate. I've had my electron and my positron come in, annihilate each other, turn into a photon. That photon produced an up and an anti-up. Those guys then came back together, annihilated, turned back into a photon, which then pair produced my final electron and positron. And this is a much more complicated, but also allowed diagram. And so what you can do is you can add as many vertices as you like in the intermediate. And you can make these things as complicated as you like. And so this is where I'm starting to say that if the total probability for this scattering to occur, I need to consider all possible intermediate things and then sum them up and then square it to get a probability. That, I mean, all possible intermediate things is infinitely many intermediate things. But again, ultimately, to calculate these probabilities, each piece of this diagram is going to be associated with some mathematical quantity. And in particular, each of these vertices, which I mean is like the dot at the center, each of these vertices is going to carry a factor associated with the strength of the interaction. And so these are all electromagnetic vertices. And so they're going to be proportional to the strength of the electromagnetic force, which is actually a weak force. And it's weak in that each additional factor is going to be less than 1. It's going to carry a factor of 1 over 137, a fine structure constant. And so the more of these vertices that I add, the smaller the amplitude I'm going to have associated with that diagram, if we're just dealing with, for instance, electromagnetic interactions. And so the more complicated diagrams, the more vertices that I add, the smaller a contribution to my ultimate probability will that diagram have. So at the end of the day, we only need to calculate sort of a finite number of diagrams, and that'll be sort of good enough to some degree of precision that we care about, and that's dictated by the experiment that you're doing. How precise is your experiment tells you how precise your theoretical prediction needs to be. Now, as I mentioned with the strong force, this sort of way of thinking about things is totally going to break down, because the strong force vertices are going to carry basically something a factor of order 1. And so more complicated diagrams are not going to contribute less. And so then it starts to sound like you really need to calculate an infinite number of diagrams in order to do anything with that involves the strong force. And so we're going to have to think about the strong force differently. But for now, in general, again, if you know that there's only electromagnetic and weak force at play, you know that more complicated diagrams are going to matter less. And so we won't have to worry so much about calculating them. Okay, so in summary, the name of the game with Feynman diagrams is that Feynman diagrams are these cute pictures, which feel very physical, but really what they're representing is each piece of the diagram, like each leg in this vertex, and then each vertex itself is going to represent sort of a mathematical quantity in a much larger mathematical expression. And so in a way, these diagrams are actually a useful way of organizing what would be a very complicated calculation. We will not derive how each piece of each diagram is associated with what calculation and sort of why, because that requires a full course in quantum field theory. But we will see, okay, if we have this leg, it's associated with this mathematical quantity. And so that tells us how we can actually calculate these amplitudes and ultimately probabilities associated with these different processes. All right, so that's Feynman diagrams.